Well, all right, guys, I think I'm going to go ahead and get started. I see most of the class is here. There's a few people still wandering over. I hope that you can see me and hear me all right, like usual. And of course, my little whiteboard here in the background, I've got a recap. If you're just coming in, you might want to start by jotting that down, just a summary of something from Tuesday that we're going to use today. Hope that you guys are all doing well. I sent you an email yesterday about the grading options for this class that the university is going to use, which I think is a very good idea. If any of you have any concerns about your grade, where you stand in the class, how you're doing, I just want to reiterate that I'm more than happy to talk to you one-on-one, either through email or through Zoom. And we can talk about how you're doing and where things are going. But you do have some more time to decide about whether you think you should withdraw from the class. I don't think that's very many of you, but if you have concerns about that, and then also you have time to decide, actually until after class is over, to decide about whether you'd like to change your grade to credit, no credit. Just this semester, they're being really flexible about that, which I think is great. So that should make things a little less stressful in light of everything that's been going on. As for where we're at in the class, we're just trucking right through chapter 8 right now, the second to last chapter that we have to cover for the semester. And I sent you a Dropbox invite to submit homework that is due tonight. I'm going to take some questions on that homework, if there are any, in just a little bit. And I'm also going to be in my office hours this evening. So if you are having any problems with the homework, by all means, definitely feel free to either ask me during our session today or later on tonight, and I'll help you with that. There is another assignment that will be due on Tuesday, and that will cover section 8.3, only section 8.3, which is what we're going to talk about today. Section 8.3, I have full, already pre-recorded video for, because I made videos of the material in that section last year. You'll find those videos on the videos tab of my website, so you can watch that stuff again later. Of course, I'm also recording this session right now, so this will also go up under the class lectures part of my website. But before we get to section 8.3, I'm going to do a quick recap, a little bit of a warm-up problem here that's actually taken from a group work, and then I'm going to take some questions on the homework that you might have that's due for today. So does anybody have any questions for me before we kind of dive into the math here? Thanks for all your hard work. I know that it's hard to stay focused with everything going on. My grader is working on the papers you turned in on Tuesday. I'll try to get those back to you as soon as I can. And again, we have another assignment for tonight, which should be a little easier, by the way. If you haven't finished today's homework, I don't think it'll be quite as lengthy as the one that you did for Tuesday. Okay. What I put at the top of the board here is a theorem that I mentioned on Tuesday, and I just want to remind you about this again. When we're looking for a basis consisting of functions, which is what we're doing in chapter 8, because let me just back up for a minute. Chapter 8 is about differential equations. So the vectors that we are interested in are going to be the solutions to those differential equations. And those solutions are functions. So the functions, I'm going to call them, y1 through yn, right? The question is, if we want to make a basis worth of solutions to a differential equation, we have to know that those functions are linearly independent, okay? Now, if there's only two functions, it's pretty easy, right? When you have two vectors and you want to know if they're linearly independent, you can just ask, are they multiples of each other? Are they scalar multiples of each other? And that's usually something that just at a glance with your eyes, you can see whether two functions are scalar multiples of each other. But what if I have a bigger list of functions? say y1 through yn, right? This is where this Wronskian theorem comes in, okay? What this theorem says up here at the top is that if you calculate the Wronskian of your functions, and if you can choose a number, let's call it x naught, such that that Wronskian is not 0, then you're good, right? Then your functions are linearly independent, okay? So I thought we would practice this theorem, and it'll help us to remember what the Wronskian is and everything, by doing this warm-up problem that I've got on the board here. We actually kind of used this rather liberally on Tuesday, even though we hadn't really verified this yet. But let's say that I write down the auxiliary equation for my, nth order linear constant homogeneous constant coefficient homogeneous differential equation. We write down that auxiliary equation, and let's say we find 3 distinct roots, A, B, and C. So we get 3 real numbers that are all distinct. Okay, so on Tuesday, without really justifying it, I just said, well, you know what? Those functions are going to be linearly independent. So to start off today, just to practice this Wronskian and practice the theorem at the top of the board, I thought, let's just verify this, okay? So this is actually off of group work number 12. I'm kind of doing group work number 12, problem number 1 right now. So this is already typed up and it's on the website, but let's just work it through together, okay? So the claim is that if we have 3 distinct roots, A, B, and C, to our auxiliary equation, then e to the ax, e to the bx, e to the cx will be linearly independent, okay? So to do that, to show that, what I'm going to do here is I'm going to calculate the Wronskian. This is the thing that I call W. And W, if you remember, W is just the determinant. It's just the determinant of what you get. Remember how you fill out the Wronskian? You put your functions on the top row, e to the ax, e to the bx, e to the cx. Those are my original functions. And then you start taking derivatives down the matrix. So when you differentiate these exponential functions, you're just going to be bringing down the a, the b, and the c. Okay, and we're going to do that twice because we have to make a square matrix out of this. So this is what you're going to get for your 3 by 3 Wronskian matrix, right? So you're taking derivatives of the functions on the top row, and then the second derivatives go on the last row. And it's a 3 by 3 matrix now. So we can take the determinant. For a 3 by 3, in this case, I would just use the arrow method. So you'll remember that for the arrow method, normally, if you need to, you can just recopy the first 2 columns of your matrix off to the right here. And then we just do our arrow multiplications. Now, what I want you to notice about all 6 of the arrows is every single, let's just look at the first one actually. E to the ax times b e to the bx times c squared e to the cx. Every single one of my 6 diagonal arrows that I'm going to find when I do the determinant is going to have a factor of e to the ax, e to the bx, and e to the cx. Do you see that? You go down this first diagonal, we have e to the ax, e to the bx, e to the cx. The next diagonal, e to the bx, e to the cx, e to the ax. Every single one of my diagonals has that. So just to simplify my work a little bit, I'm going to factor that out. Okay, I'm going to factor it out. I have an e to the ax, an e to the bx, and an e to the cx. I'm going to factor that out of all 6 of my diagonal products, okay? And now what am I left with here? The first diagonal is bc squared. The next diagonal is ca squared. And the next diagonal is ab squared. Okay, then we go the opposite direction. Remember, we subtract. What's this going to be? It's going to be a squared b, and then minus b squared c. Whoops, there should not be a bracket there yet. We're not ready for that. And then the last diagonal is c squared a. So there's the Wronskian for you, okay? Now, this part in brackets kind of looks like a bit of a jumble of letters. And whenever I do this group work in class normally, because I use the same group work every semester, everybody gets stuck at this point because they're like, oh, I don't know what to do with this part in the brackets. It turns out that it simplifies very nicely. Actually, I don't know if I want to erase my theorem quite yet. Let me just erase this middle part. Okay, so I'm just going to come right back up here and finish this. So I have e to the ax, e to the bx, e to the cx. And now here's the thing that everybody always gets stuck on the part in brackets, but I'm going to tell you what it comes out to. It's just an algebraic thing, so it's not really conceptually that important for you to worry about. But what it comes out to is, it comes out to c minus a times a minus b times b minus c. As it turns out, it's a triple product of those things. If you were to FOIL those terms out, you would get all of the terms that you see down here at the bottom. Okay, so right, so that's kind of just something to take note of. Happens to work. Now the thing of it is, if you believe me that this triple product here is the same as what's in the brackets, just take my word for that. Now it's easy to see that nothing in this line, no part of that line is zero. Exponential functions are never zero. Remember that my three, I just erased the question, but the a, b, and c are all distinct. That's the assumption. They're all different. They don't repeat. So none of these subtractions are going to be zero. This whole Wronskian is not zero. Nothing on that line is zero. A bunch of non-zero things are being multiplied together. Okay? And so thus, e to the ax, e to the bx, e to the cx is Li. Now, as I mentioned, guys, for your homework, you don't need to be checking this Wronskian on every problem, right? You don't need to actually verify the linear independence because, as I mentioned on Tuesday, this has all been done historically. Mathematicians and engineers and scientists have needed to know that these functions are linearly independent for literally for centuries. There's no need for us to go back and reinvent the wheel. So this example was really just to practice the Wronskian. I do want you to know what the Wronskian is and what it means. But you don't have to think that, oh, every single homework problem, I have to go verify this determinant is not zero. Okay, you can kind of take it easy on that part. Okay, are there any questions on this little warm-up problem? Okay, great. You know, I had another thought before I erase the theorem here. I'm going to try to erase my board. It's not always so easy. Just slide this down just a little bit here. Maybe my project over the weekend, I'll try to figure out how to get this board a little bit better stabilized so I can put a little more pressure on it to erase it. Anyway, I had a little thought here, and this is also kind of theoretical, so I'm sorry for all the theory stuff right at the beginning today. But it might be useful for you guys to understand why this theorem is true. So I think I'm going to actually write down a proof of this for you. And this is actually also in the group work. These two examples that I'm starting off with today are from group work number 12. So I'm going to go ahead and prove this theorem. That's the second group work problem on group work number 12. The reason that I think it's kind of good for us to see the proof of this is we're proving that a set of functions is Li. And I think it's nice to review what linear independence means, right? Because it does come up a lot in chapter 4, and we are going to need to know this for the final exam. So let's just go ahead and give a proof of this theorem. And again, you can go to group work number 12 and see more details on it. Okay, and I mean, you can see the whole thing written out there as well. Okay, so how do we prove that a set of vectors is linearly independent? This goes back at least a month now. Linear independence, what it means is that if my vectors cancel out in a linear combination, if we can cancel out a linear combination of the vectors to 0, then all of the scalars of that combination have to be 0. So the way that would look, if I was to write it down, is I would assume that C1 times Y1 plus C2 times Y2 plus ... plus Cn times Yn is equal to 0. I would start with that assumption, and I want to show, let me write it down. We will show that all of these constants are equal to 0. Right, so we're going to try to show that all of those constants are 0. So I'm going to start from here. Let me put a box. I'm going to start from that equation. This is the way linear independence is proven in a theoretical context. I know back in chapter 4, when we had specific vectors, we would lay them out into the columns of a matrix and do a whole process of elementary row operations and highlighting pivots and free variables and things like that, right? But when it's abstract and theoretical, like this theorem is, this is really our go-to approach, right? Assume we have a combination of our vectors, which are the y1 through yn, and assume that it cancels out to 0. Okay, right over here. I'm going to try to show that all of the constants are 0. The thing is, what we can do with this box, guys, is we can just start taking derivatives of it. Y1 through yn, they're all functions. We can differentiate them. So I would have C1 Y1 prime plus C2 Y2 prime plus ... plus Cn Yn prime. This is also equal to 0. Right? Just take the derivative of the first box and you get the second box. And you can keep doing that. You can take as many of these derivatives as you want. In fact, let me just keep going, ... here. For reasons that you're going to understand in just a minute, I'm going to keep going until I get to n-1 derivatives. So let me write this down. C1 y1 to the n-1 derivatives plus C2 y2 to the n-1 derivatives plus Cn yn to the n-1 derivatives. That's all equal to 0. So we're just creating more and more equations by just taking more and more derivatives. But if you take all of those boxes on the board and you say, I actually would like to combine them into a single expression, can we compactly take these equations and make them into a single expression? This is where matrices can be used, right? We can actually use matrices to do that. Let me come over here and show you. This is really again, showing the power of linear algebra to helping us understand something from differential equations. So if I actually put all of this into a matrix, right, what I'm going to do, I'm going to put y1, y2, and so on. I hope you can read that. I'm a little bit short on room here. Y1 through yn. I'm going to right multiply it by C1 through Cn. Yeah? See, the thing is, if you actually multiply this out over here, I haven't filled out the whole matrix yet, but if you multiply that out, do you see that you get the left side of the top equation? You're just going across the, sorry, I got to get myself. You go across the rows of the first matrix and then down that column, right? Down that column. So it's like this. It's just dot products. You get the left side of the very first equation on the board. So this is equal to, I'm going to squeeze it in here. There is a 0 in the top entry on the right-hand side. Okay? Now the second box is very similar. It's the same thing except with the derivatives of those y's. So y1 prime, y2 prime, all the way up to yn prime, and that equation is also equal to 0. So what you're getting, and I know it's a little hard to read, the right-hand side here is just a big column of zeros. And you're just creating exactly this matrix that I think should look familiar. Y1 up through yn with various derivatives. That matrix, this n by n matrix here, is exactly related to the Wronskian. The Wronskian is the determinant of that matrix, right? What are we assuming in this statement at the top? Suppose that the Wronskian is not 0 for some value of x. In other words, suppose the determinant is not 0. Now, guys, if the determinant is not 0, it means that the matrix, this matrix, is invertible, right? So let me write that down. That matrix is invertible. So this is invertible since the Wronskian is not 0. We're assuming that the determinant of that matrix is not 0. So it's invertible. If it's invertible, we can basically cancel it. We can take the inverse of that matrix and cancel it. What happens when you cancel it? When you cancel the matrix, let me write it here, canceling the matrix, again, we're doing that because it's invertible. So canceling the matrix, we get, what do we get? We get C1, C2, dot, 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 up to Cn equals all zeros. And that's exactly what we wanted to show. We wanted to show that C1, C2, C3, and so on, all of those constants are 0. And so we get that now. We basically just invert the matrix, which cancels it from this equation over here on the far right. And now that tells me that all of the constants are 0. So this is a nice proof to do because it reminds us about what linear independence entails. And it's nice to prove things just so we know why things are true instead of just being handed everything without a justification. So, all right, so whether you know it or not, in this first few minutes of today's class, I've basically gone through group work number 12. There are 2 problems on group work number 12, and the first one was that warm-up problem. The second one was the proof of this theorem. So we're up to date on that group work, and it's a little more of a theoretical group work than some of the ones that I've asked you to look at in the past, but I hope that it's been useful. Are there any questions here about this Wronskian theorem? Okay, if not, what we're going to do next is I'm going to take questions on today's homework assignment, if there are any. So while I'm erasing the board, maybe you guys could get out your homework, take a look at how you're doing with the assignment. If there's anywhere that you're stuck, we can make a list of problems, or you can just shout out, unmute yourself and ask me. So give me a minute to erase the board, grab your homework, and let's take a look at it. Okay, it takes a little while to get that done sometimes. Okay, I see a couple of questions that people have already put into the Zoom chat. So let me start with those, and then in the meantime, if there are others that come up, we can also look at those. So we're looking at 8.1. Let me look at problem number 10. This is a good one to look at. Number 10. It asks us to find the kernel of L, where L is D minus 3x squared. So remember that the kernel is just those inputs to the function that get killed by the transformation, right? So in other words, we want to basically, the kernel of L is just the set of y such that L of y is 0. That's what the kernel means. So let me take this equation L of y equals 0 and see what it gives me. So if I plug that in, I'm going to get d minus 3x squared of y is equal to 0. Right? So you're just applying L to y, and you're going to set that equal to 0. And what we're trying to do right now is solve for y. Yeah, that's the whole thing. We have to solve for y. Remember that d just means derivative. So here I have d of y. I'm going to write it in this prime notation for a minute. So it's just y prime, and then minus 3x squared y equals 0. So you literally just distribute the terms of the operator to y. Okay? Now, what is the order of that differential equation? It should just be first order, right? It's only first order. And where did we learn about first order differential equations? Well, this was back when I was in California, the very beginning of the semester, right? The first 2 weeks, we learned in chapter 1 how to solve separable, linear, Bernoulli, and homogeneous differential equations. Does anybody recognize this? Does this equation happen to be separable, linear, Bernoulli, or homogeneous?
It's separable, right?
Yeah, that's right. This is separable. That's absolutely right. It is separable. In fact, let me rewrite this. Usually when we have a separable equation, I'll write y prime as dy over dx. Let me put the 3x squared y on the other side of the equal sign. And now I can separate it. That's exactly right. So I'm going to separate this one. I'm going to put the y on the bottom of the left side, and I'm going to pull the dx up to the right side. So this is just separating the equation. And now we just have to integrate both sides, right? This is back to old times. This is what we learned way back at the beginning of the semester. So we put an integral sign in front there. And the integral on the left, when I integrate dy over y, I'm just going to get the natural log, right? So the natural log of the absolute value of y. And on the right side, when I integrate 3x squared, well, I just get x cubed. And I'll put my plus c over there on the right side as well. So we just get the absolute value of the ln of absolute value of y equals x cubed plus c. And now it's just a matter of solving for y. So we've done this kind of thing before, right? It's just algebra. I'm going to exponentiate both sides, right? So I'm going to apply e to both sides. That's going to cancel my ln. So I'll get, you know, absolute y equals e to the x cubed plus c. And of course, I can rewrite that as c1 times e to the x cubed. So again, splitting up that if we split up this plus sign right here and we change e to the c to c1, that's what we're going to have. Okay. Finally, I just have to remove the absolute value bars. I can do that simply by putting a plus or minus in front of that c1, which just can be relabeled as c2. So y equals c2 e to the x cubed. Okay, and that's basically it. So your kernel of L is just basically, in this case, I'll just put it here. It's the set of c2 e to the x cubed such that c2 is a real number. That would be one way you could just kind of write it as a final answer. Okay. Is that good with everybody? Any questions?
Yeah, thank you.
You're welcome. Anybody else stuck on this at all, or does it most of the work make sense? Okay. If so, then we have another question that was listed here, which is number 2 on the same section. I'm going to go ahead and erase this. If anybody's not done copying it, you're just going to have to come back and either figure the rest of it out on your own or watch the video later on this afternoon. I'll post this to my website immediately after class today. So let me erase this so I can give myself room to do number 2. Okay. Number 2 is a problem where they give you an operator. They give you an operator and then they just ask you to plug some things into it. I don't want to do all of these parts. Reza, do you have a particular part, A, B, or C on number 2 that I could do? I don't want to do everything on this one. Maybe just one part only.
Professor, I was confused on part C.
Okay, I'll look at part C with you then. So number 2, L equals d squared minus x squared d plus x. So this is a linear operator, okay? So actually, in part A, they give you y of x equals 2e to the 3x. And they ask you to figure out what is L of y on part A. So you have to take, you know, 2 derivatives of this and then minus x squared times this and then plus x times this, okay? So you work that out right there. And then on part B, they give you a different function, which is 3 ln of x. And they ask you to do basically the same thing. What is L of that function? So actually, for part C, if you take a look at part C is actually just a combination of the first 2 parts. What they're asking you, if you take a look at part A and part B, they're just adding those results here. Now remember that L is a linear transformation. It respects addition, right, and scalar multiplication. So if it respects addition and scalar multiplication, then for part C, all you have to do is take your, you know, answer to part A and your answer to part B and add those together. So you don't actually have to start over and take a bunch of derivatives again. You can use the fact that the function in part C is just the sum of the functions in parts A and B. So whatever those answers are, you're just going to add them here. Does this make sense?
Yes, thank you so much.
You're welcome. Does anybody need me to or want me to work out what these answers are, or is everybody okay with how this operator works? Okay. Hearing nothing, I'll assume. Oh, yeah. Somebody wants me to do it. Okay. Let me do part B. I'll let you try part A later, but let me just do part B. I'm going to do it right down here at the bottom. We're going to apply L. So let me write down L here. It's d squared minus x squared d plus x. So this is what L is. And we're going to apply that to 3 ln of x. Okay, so this is the y right here. So you sort of have L of y right now. Okay, so how does this work? Well, we're going to just distribute these terms, right, of the operator. So d squared of y is just, let me just write it this way for now, 3 ln of x double prime, and then minus x squared times d, which is one derivative of 3 ln of x. And then finally, the last term, which doesn't need to be simplified, is just 3x ln x. Okay, so this is, sure you can see that there. This is what you have to do. The last term is already done. And you just have to take, I guess, 2 derivatives of the first term here. The factor of 3 can be pulled out, of course. Derivatives respect scalars. If I differentiate the ln of x twice, the first derivative is 1 over x. So when you differentiate it again, you should get negative 1 over x squared just by the power rule for derivatives. Okay, and then minus the second term, which is x squared, times the derivative of 3 ln of x, which is 3 over x. And then the last term just gets, the last term just gets recopied, 3x ln x. So just something like that. You could clean that up a little bit. You don't really need to simplify these expressions that much. But does that make sense, Omar and everybody else? Is that good? How you do that? Okay, great. So yeah, so that's part B. You also just have to do part A, and then for part C, you just add them together. You don't actually have to do any extra work at that point.
So, Professor, for part C, we don't have to simplify it all the way down, right?
No, it's not really necessary to simplify these. We're kind of just practicing how these operators work. I don't want you to end up spending like lots of time just on algebra. This is not a class on just algebra. So I just want to know that you understand how to use the operators. This is the important thing. Okay, does anybody have any other questions on today's homework that they'd like to ask me? I'm happy to look at it a little bit more. Marian, can you give me a specific problem from 8.2 that you're talking about initial problems? It must be the ones near the end. Maybe you can give, 35. Okay, yeah, let me take a look at 35. I appreciate your patience with me while I'm trying to get these boards cleaned off. Okay, so 35 in section 8.2. Let's look at that one. What we have is y double prime minus 8y prime plus 16y equals 0. And then we have an initial value over here. So we haven't seen one of these in a while. Y of 0 equals 2, and y prime of 0 equals 7. And they want us to solve this, okay? We did a little bit of this kind of thing in chapter 1, where we were given an initial value to a differential equation. The idea is that you leave the initial conditions to the very end. So you don't worry about them right away. Instead, you just concentrate on solving for the general solution to this differential equation right here. Okay, so of course, the first thing to do here is to, as we learned on Tuesday, is you want to write this in operator form, right, using the D notation. So in other words, you're going to re-express your differential equation with your unknown function y on the outside. And then in here, in these parentheses, is where you're going to write down your derivative operator. So y double prime, that would be d squared, and minus 8d, and then plus 16. So this is how this should look, right? Remember that on Tuesday, I showed you that if we guess the solution e to the rx and plug it in, we get an auxiliary equation. I'll just put it here. An auxiliary equation where all of the d's just turn into r's. So some of you might be able, and I'm perfectly fine, you might be able to go straight from the original problem straight to this. If you don't really need to write down the middle step, that's okay. It's easy enough to see what's going to happen. But you do have to factor the auxiliary equation. This one is a quadratic. Quadratics are not so bad. We can just use the quadratic formula, or in this case, you probably might have noticed that it just factors really nicely anyway, r minus 4 quantity squared. And that tells me that my roots are 4 and 4. We have a double root of 4. So let's go to the general solution now. Y of x equals, so we're going to have C1 times the first solution, which is e to the 4x, and then C2. Now, remember from Tuesday, this is a repeat root right now. The 4 is showing up right now for a second time. So remember how we handle that. When a root gets repeated, we start stacking x's in front of the exponentials that we have. So in this case, I put another x here and then e to the 4x. So this is the general solution. Pretty easy, right? Nothing too crazy about that one. After all, it's only a second order differential equation. We have two constants here. And so this is the initial value part now comes in. We can use these initial values to solve for C1 and C2. So for example, I know that y of 0, if I just put 0 in for x, I get C1 times e to the 0 plus C2 times 0. So I just get C1, but I know that that's supposed to equal 2 because that's what was given to me up there in the assumptions. Okay, and then what about this? What about the y prime case? For that, we actually should take the derivative of this box. If I take the derivative of the box, I'm going to get 4c1 e to the 4x plus, here I'm going to use the product rule. So this is a little annoying. I have to use the product rule on x e to the 4x. First term times the derivative of the second plus the second times the derivative of the first, right? So you should get 4x e to the 4x plus e to the 4x. That's just the product rule being worked out. Okay. So this is the derivative of y. That's the derivative of y. So now we need to plug in 0 into that derivative because we were told that this should equal 7. That's the given initial value. So if I plug in 0 here, just going to plug in 0, what are we going to have? Well, we're going to get 4c1, but remember c1 was 2. So we get 4 times 2, which is 8. Plus, in the second term, when I plug in 0, I just get, in the brackets, I just get 0 plus 1, right? 0 plus 1, which is 1. So this is just plus c2. So 8 plus C2 should equal 7. And that tells me, hopefully if I did my math right, that tells me that C2 is -1. Okay? So I know what C1 is, and I know what C2 is. And now all I have to do, you should not stop there. Be sure to write down the final answer now. The final answer is just going to be, we just come into here and we plug in the C1 and the C2. So y of x equals 2e to the 4x minus x e to the 4x. Okay, and that would be what we call a particular solution now, right? So we have the general solution. This one over here, just to remind you from way back in chapter 1, when we plug in initial values, we're going to end up getting a particular solution to the initial value problem. Okay, is this good? Any questions on this one?
Thank you.
You bet. Okay, does anybody want me to solve another problem? Okay, if not, that's great. This assignment isn't too bad. I hope it won't be too bad for you. Again, if you are still working on it, which I imagine many of you are because I haven't gotten very many submissions to my Dropbox folder yet. If you're still working on it, please feel free to ask me questions in my office hours later on tonight. I'll be glad to help you out. What I'm going to do next is I'd like to take like a 10-minute break. I'm going to get this board erased off, get myself a glass of water, and then we're going to do 8.3. Okay, this is the next section. We're going to cover section 8.3. We've got the group work done. We've got the homework in pretty decent shape, I hope. So let's take a 10-minute break, and just right before 1 o'clock, I'll be right back, and we'll start talking about what 8.3 is about. Okay, so go ahead and take a short break. the way they Bernoulli in California, but this is not one. Terrible snowstorm. Seems every Thursday we get storms.
Professor, we couldn't hear you what you said.
Oh, I was just. Can you hear me now?
Yes, right now I can hear you.
Oh, okay. I was just saying we're having a terrible snowstorm outside. So it snowed like more than 1 foot since last night. So I'm just happy to be inside doing this right here.
It's very hot over here.
Is it? Oh, well, it's not
Yeah.
hot here. Trust me. I actually got my fireplace going last night. I got a cup of hot chocolate and kind of cozied up to try to stay warm. Yeah, it was good. It was good. I had a nice evening. Yeah, when you live in the mountains, you don't get warm weather till like June. So right now I'm still trying to break out of winter. I'm actually looking forward when the sun comes back out. It's going to be spectacular. I'll probably try. I think tomorrow it's supposed to clear up a little bit. I'll probably try to go out into the snow and go on a little adventure or something. That should be good.
I like going to the snow.
Yeah, it's one of the great things about California is you can have that nice sunny warm weather, but then you can also just go for like 1 or 2 hours. You can be up in the mountains, and so you kind of have everything there. Where I am over here, I don't really have a fast place to go that's warmer. I guess I could drive down to Denver, but that's not going to be quite as warm as LA, I don't think. So.
Yeah, my family and I, we usually like rent a cabin up at Lake Tahoe, but I don't think we're.
Yeah, Lake Tahoe is great. I usually go there once a year. There's a math conference in Tahoe. Can you guys still hear me okay? I've got some message telling me my audio is.
Yeah, we can hear you.
Okay.
I can hear you.
Okay, I don't know why my screen is saying my audio is not working, but anyway, okay. Let me know if it looks like I'm talking and you're not hearing anything. Somebody needs to get my attention. Maybe I walked over to the window and confused my computer for a minute. I'm not sure why.
She's remembering to tell you so she saw you dance.
Yeah, it's very cold here. That's why it's nice to make a fire and just get kind of cozy, get some hot chocolate going. I've got the heater turned on in the house. It's very different probably from where most of you guys are at right now. The laptop was cold. I don't know. Maybe. All right. Well, I think I'll go ahead and get started again. I hope everybody's made it back from a little break. Somebody was asking me when the next homework is due. I have posted it already on my website. It is due next Tuesday. The next assignment is due on Tuesday, and it's only this one section that's going to be covered. So 8.3. The title of this section is Annihilators, and you'll understand that title very soon. We're going to be annihilating functions like crazy. And again, I have all of this stuff already video recorded on my YouTube channel, and I made links to those on my videos section. So you can always rewatch that, or you can just rewatch this as well, because it's going to be the same thing. Okay. All of the stuff we did in the last section, we were looking at differential equations that were homogeneous. They all had a 0 on the right-hand side. What we're going to do in this section is we're going to relax that requirement, and we're going to go back to looking at the more general non-homogeneous equation. So the goal in this section is going to be to solve L of y equals f for y. So we're going to change that 0 that we had up there before. We're going to change it again to a y. So we're going to try to solve for y. Y is my unknown function. And there are going to be 3 steps to doing that. There's 3 steps here, okay? The first step, step 1, is to solve the corresponding homogeneous differential equation. This would, of course, just be L of y equals 0. So, in other words, just go back to the last section and solve the corresponding homogeneous equation. Forget about the capital F, change it to a 0. When we do that, we're going to get a solution that is called the complementary function. And the notation for that is going to be, we're going to call this solution y sub c of x, and this is called the complementary function. Okay, so that's the first step. Step 1 is to just go back to what we learned before in section 8.2 and figure out the complementary function. Okay, so that we already know how to do. That's what we've been practicing. Step 2 is to find one, and we only need one, find one particular solution and that particular solution is going to be denoted y sub p of x. Find one particular solution to L of y equals f. Okay, so that's the next step. Okay, find one particular solution. You only need one, and that's the part that I'm going to have to explain in a moment. That's kind of the new part for this section. And then the third step is to write down the final answer. The final answer is just y of x equals y sub c of x plus y sub p of x. In other words, you just have to add together the complementary function and the particular solution. You just add them together. Okay, so step 3 is really just the housekeeping at the end to kind of clean up the final answer. The real new work for this 3-step process is step 2. So I'm going to talk about how do we do step 2. Okay, so where did my eraser go? Here it is. Okay, so this is just the overview. This is the overview of the 3 steps that we're going to use to accomplish our goal. Okay, so let me come up here and I'm going to talk about how to do step 2. Okay, so to do step 2, let's put this here. To do step 2, we are going to use annihilators. And those annihilators are going to normally be written as A of D. So when I talk about an annihilator, in terms of notation, I'll write it as A of D. How does it work? Well, here's what we're going to do. our differential equation, actually, I'm just going to scribble down here. You don't need to write this down yet. But here's the equation we're trying to solve, right? That's what we're trying to solve. Now, on Tuesday, we learned how to solve this equation if f was 0, right? Section 8.2, the previous section. If the f is 0, we're good to go. We just find the auxiliary equation, we write down the roots, and boom, we can put down the general solution immediately. So what we're going to do is we're going to annihilate, if we can, we're going to try to annihilate capital F and make it 0. Okay, we're going to somehow try to make it 0. And this annihilator, as you can see in the top right notation, this annihilator is going to involve the derivative operator. So we're going to try to annihilate capital F by using derivatives. In other words, we're going to try to use derivatives to make capital F become 0. Let's see, for example, if I had a function, let's say capital F was x squared. If you take enough derivatives of x squared, it'll eventually be 0, right? You will have annihilated x squared by using derivatives. In that case, you would need 3 derivatives, right? So if you differentiate x squared 3 times, you get 0. This is the idea, is we're going to apply an annihilator to our differential equation, hopefully so that we can annihilate capital F and then go back to what we learned in section 8.2, the previous section where we had a 0 on the right-hand side. So let me write some of that down, right? What we're going to do is how do I want to say this? We are going to find an operator A of D such that A of D applied to capital F is 0. This is the whole idea. Let's just annihilate capital F. Okay, now let me give you a couple of examples of annihilators, and then once we've got a couple examples in mind, we'll go to some actual differential equations and try to solve them. Okay, so just as an example, I guess I already did one. So the first example is, so if capital F of x is equal to x squared, then to annihilate x squared, I should take 3 derivatives. So the annihilator of x squared is just d cubed. D of d of d of x squared will be 0. More generally, I think you would agree that if f of x is x to the k, where k is a, let me just say, k is a positive integer. K is a positive integer. In this case, A of D is just D to the k plus 1 power. So if I want to annihilate a power of x, I'm going to need to take one more derivative of it than what that power is. Okay, so this is just kind of in general, this is what you would expect. Okay, let's think of some slightly, by the way, interrupt me if there's any questions so far. Right now, I haven't really explained how we're going to actually do step 2 yet. I'm just trying to get a handle on what these annihilators are all about. Okay, let's do another example that's a little bit harder, but feel free to jump in with a question about this if you have one. Okay, so what if f of x was, I'm going to write e to the ax. Now the thing with that is If you take the derivative of e to the ax, you just pull an a down. And if you take another derivative, you pull another a down. You actually are never going to get 0 by just taking derivatives. If you take the derivative of e to the e to the ax over and over and over again, you won't get 0. You'll just get e to the ax times some factors of a that are piling up in front, right? But what we can do is we can still annihilate this as follows. You see, if you take one derivative, let's do that. If we take one derivative of e to the ax, we get a e to the ax, which is just a times the original function. So if I subtract those results, if I take d minus little a, I'm going to get 0. Let's just make sure that you understand that. If I take d minus a and multiply it by e to the ax, right, we should get 0. The derivative of e to the ax minus a times e to the ax, that is 0. Right? That does cancel out. So these basic exponential functions are pretty easy to annihilate. Okay, those are pretty easy to annihilate. Let's do another one. Let's do f of x equals the cosine of bx. All right. So just take cosine. Again, if you just take derivatives of cosine over and over again, you're just going to flop back and forth between sine and cosine, and you're never going to get 0. So it's a little more complicated. But one thing I do know is that if I take 2 derivatives of cosine, right, after you differentiate cosine twice, you get back to negative of cosine. Right, there's a sign change after you do 2 derivatives of cosine. So I'm going to guess that we can annihilate the cosine of a function by somehow involving 2 derivatives. Somehow with 2 derivatives that we should be able to do this. Okay, so it turns out that that's absolutely true. Sorry, I am just going to do something really fast. So the thing is, when I take 2 derivatives of cosine, what am I actually going to get? I'm going to get cosine of bx with a minus sign, and there'll be 2 factors of b that come down as well, right? So there'll be 2 factors of b because every time you differentiate this bx, there's a b that's going to come out. So to fix this, what we have to do if we want to get it to cancel out is we have to do d squared plus b squared. And again, we can check this. If I do d squared plus b squared times the cosine of bx, okay, what does this mean again? This just means 2 derivatives of cosine of bx plus b squared times cosine of bx. And if you take 2 derivatives of cosine of bx, you're going to get negative b squared of cosine of bx. This actually cancels out to 0. This is equal to 0. The whole thing is equal to 0 there. Okay? So hopefully everybody's with me so far on this. We've done just a few examples. The same thing is true, by the way, for sine of x. In fact, let's go back. In fact, I'm going to erase this little calculation at the bottom. Okay, this is just verifying that my annihilator is correct. I'm going to erase this, and I'm just going to insert right here sine of bx. It works the same way. Derivatives of sines and cosines are kind of more or less the same sort of pattern. Okay, So we know how to take derivatives of powers of x, right? E to the ax and sine or cosine of bx. If our capital F happens to involve powers of x, e to the ax, or sine or cosine of bx, we should be able to annihilate it. And in fact, we can even do combinations of powers of x, sines and cosines, and e to the ax. What I'm going to do right now with you guys, I'm going to share my screen with you to show you a handout really fast, okay? So let me see if I can pull this up. This is, hopefully you can all see what I have in front of my screen here. This is a table, it actually has integrals on it as well, but it's mainly for right now, I want you to focus on the top part of it, which is a list of some annihilators. So you can see right there the annihilator of x to the k, the annihilator of e to the ax. But then as you go down the list, you see some slightly more complicated ones that have combinations of powers of x, sines and cosines, and e to the ax. And by the time you get to number 8 or number 9 on that sheet, it's a pretty messy annihilator. Okay, here's the deal, guys. I'm not going to ask you to memorize the annihilators. I am going to be giving you this piece of paper. You're going to be allowed to use this table of annihilators and integrals on our third midterm as well as the final exam. So there's no need to struggle to memorize this one. This is actually a handout that you can find on my website. There's a link. One of the links that's on my 250V website says special handouts, and this is the one that's right at the top of that page. So if you want to go print it out just so you have it in front of you for the homework or whatever else, by all means feel free to do that. This is something that you're allowed to use, okay? It's really hard. For example, look at number 9. The annihilator of x to the k, e to the ax, sine of bx. You're going to annihilate that just by taking derivatives. This is going to be pretty messy to do, right? There's horrendous product rules involved and everything else. So there's no way that I'm going to be asking you to derive these annihilators. So you're more than welcome to just use this handout. Okay, so that handout, we may need it a little bit today, by the way, on our examples. So I'll pull it back up if I need to. But that handout is going to be important for this section. Okay. Any questions so far? If not, I'm going to spend the rest of the time today practicing examples of now how do we actually use these annihilators to solve differential equations. This is the fun part, okay? So let me do that. We're going to come right back up here. And we'll get some examples going. This is one of those sections where the best way to learn it is to just do examples, right? There's not a lot of theory here. We don't have to like spend forever trying to have a huge conceptual discussion. We just need to understand the process. And it's a 3-step process, and we're going to use annihilators to help us with that second step. So here's the first example. I'm going to start with a pretty easy one, and then we'll do some that are slightly harder. Okay, so let's solve y double prime minus y equals 16e to the 3x. Okay, so let's try this one. Okay, so I'm going to go through the 3 steps. The first step, and I'm going to be pretty fast and brief about some of this because it's not that bad. Remember that in the first step, we just ignore the right-hand side. We just forget about that, and we just pretend like it's equal to 0. The auxiliary equation, I'm going to go straight to the auxiliary equation here. I think everybody can see, right? This is just two derivatives. That would be r squared minus 1 equals 0. And that means we can factor that very easily. My roots are plus and minus 1. So my complementary function, right? Step 1 has the complementary function in it, is very easy to write down. Y sub c of x is just c1 e to the x plus c2 e to the negative x. This is all just review from Tuesday, right? We just find the roots of the auxiliary equation and build our linear combination that represents the solution. When you're doing the homework, guys, please put your complementary function in a box, okay? So that it's easy to find. Because we're going to have to come back to it later in step 3, right? Okay, so that's my complementary function. Let's go on to step 2. I need to annihilate 16e to the 3x. Oh, this is something I forgot to mention. Ugh, it must be the snow outside. It's messing with my head. When you have constants like 16 in front of one of these functions that we're trying to annihilate, it makes no difference. We can kind of just ignore it. If I want to annihilate 16e to the 3x, I'm going to use the same annihilator as if it was just e to the 3x. The 16 doesn't matter at all. The annihilator of e to the 3x, if you remember from what was up here before, and I know this is the disadvantage of having such a small board to work with, I have to erase everything so fast, but it's also on your table of annihilators. It's just d minus 3. It's just d minus 3. So again, if you just look at the table, you see on item number 2 here, the annihilator of e to the ax is just d minus a. So we've got it on our table. Again, if you do have a printer at home, I'd recommend just printing that page out. It's just one page. That'll be really handy for you instead of having to pull it up on the computer all the time. Okay, so how do we now use this annihilator to finish solving this problem? So we're going to take this differential equation. Let me come back up to the top. This differential equation in operator form, it's just d squared minus 1 of y equals 16e to the 3x. So let me get out of the way and make sure everybody can see that. That top right corner is the operator form of my differential equation. What I'm now going to do is apply this annihilator to both sides of the operator form of my original problem. Okay? What is that going to end up giving me? Well, that's going to give me d minus 3 times d squared minus 1 of y equals d minus 3 of 16e to the 3x. So I've literally just put a d minus 3 in front of both sides. I'm applying the same operator to both sides, so this equality, this equal sign should still be valid, right? The equal sign that we have right here is now still valid right here because I've just put a d minus 3 in front of both sides. Now, d minus 3 was chosen specifically to make 0 on the right side. D minus 3 is the annihilator of e to the 3x. Okay? So what do we now have? We have a homogeneous differential equation. It's a little bit higher order than it was before, but we can solve it just like we did in the last section because this is now a 0. We find the roots here. Now the roots, let's take a look at these roots. We have 1 and plus and minus 3. That's the roots of this operator on the left side. I would like to point something out. The plus and minus 1 roots, we had already found those before. And this is always going to be the case that the roots that you found in step 1, the roots that you found in step 1 are going to carry along, and they're still going to be here in step 2. So I'm going to be always talking about those as old roots. Those are the old roots that we had from before. The new roots are the ones that have just shown up in step 2. In this case, there's only one new root, which is 3. Okay? So if we were to now take this information and write down the sort of what the solution would look like, right? How would this all come together now? Well, let me come over here and write it down. What you would get is you would get y of x equals c1 e to the x plus c2 e to the negative x plus, and now there would be another term, c3, which would be e to the 3x. This part right here is actually the complementary function. See, you're just rederiving the complementary function here. The part that is new is that last term right here. And that is what we want to focus on in step 2. That's actually the y sub p. So let me just emphasize that. Whichever terms are new in step 2 correspond to your particular solution. So the old terms, the old roots and the old terms are going to be repeated from what you did in step 1, always. But you may get some new roots that came from the annihilator, actually. So you can very quickly see, here's the annihilator, d minus 3. What new root did that give me? Well, it gave me 3, and that term gets lumped into the particular solution. Now, here's one little thing I need to point out, though. C1 and C2, those are constants that we cannot solve for unless, like on that homework problem that we did earlier, we have an initial condition. So if we have an initial condition, we can solve for C1 and C2. But ordinarily, for just the general solution, we cannot solve for C1 and C2. However, we can solve for the particular solution specifically. So I want everybody to get their erasers out, because I do not want you to call that coefficient C3. I did that initially, but I would now want to emphasize the fact that this constant that goes with the particular solution is actually something that we can find. I'm going to call it capital A. It is a number that we can actually find. So I'm going to come back up here and erase a little bit. What else can I erase? I guess I can erase most of this. Let me just go ahead and erase this part and this. I'm going to show you how to actually solve for capital A. By the way, you probably noticed that we've already got step 3 going. Step 3 of the 3-step process just says take the complementary function plus the particular solution. It's exactly what we see here. Okay, but we can solve for A. How do we do it? Well, we just plug our particular solution. So let's plug y sub p of x into our differential equation. So what is that going to give me? That's going to be a e to the 3x double prime minus a e to the 3x equals 16 e to the 3x. So I just literally plug the y sub p into the equation. Now, if you take 2 derivatives of a e to the 3x, the factor of 3 is going to come down twice, right? You're going to get 9a e to the 3x minus a e to the 3x equals 16 e to the 3x. Pretty straightforward. And now you see that you just, these 2 terms on the left can be combined. It's just 8 a e to the 3x equals 16 e to the 3x. Cancel the e to the 3x's, and we find out that a is equal to 2. We can actually come up with this number, like we can solve for it. So a is equal to 2, so that just means that my particular solution here is just 2 e to the 3x. And then finally, step 3, which is my final answer, y of x equals c1 e to the x plus c2 e to the negative x plus 2 e to the 3x. This is the final answer with the complementary function added to the particular solution. Does this all make sense to everyone? Okay, great. I'm going to do, so this is, unfortunately, this is like a pretty easy one. Let me show you, it's not always quite that easy. Let's do another, I'm going to try and do at least a couple more examples today and show you some of the things that can sometimes come up and make it a little bit more complicated. Okay, so let's do another one that's a little bit harder. Okay, so here's another example. Let's solve y double prime minus y prime minus 2y equals 10 sine of x. Okay. Oh, the question, somebody just asked a question, why is C3, why did I call it A? You don't really have to call it A. The reason that I called the C3A on that last example was just to make a distinction between the constants that are in the complementary function that we are not going to be solving for and the constants that are actually coming up in the particular solution that we can solve for. Because people can get confused, which constants do I just leave in my answer and which constants do I actually solve for? So instead of labeling C3, if I call that constant capital A, that's going to help me remember that that's one of the constants I can find. It's really a notational issue, that's all. Okay, does anybody else have any questions before we continue? Okay, everybody can still hear me all right, yeah?
Yes, Professor.
Okay, great. My screen says my speaker is not working, so I'm like, okay. But if it's working and you guys can hear me, that's good. Okay, let's do this example right here, all right? Y double prime minus y prime minus 2y equals 10 sine of x. I'm going to write down the operator form. I think everybody's hopefully by now pretty comfortable with this operator approach, just using the d's instead of the primes. So d squared minus d minus 2 of y. And I'm going to focus on step 1. Step 1 is to just write down the auxiliary equation. I'm going to go straight to it. You just change the d's to r's. This thing factors really quickly. This factors as r minus 2 times r plus 1 equals 0. And so my roots are 2 and negative 1. Okay, I'm going pretty fast through this first little part, step 1. So I get my complementary function, y sub c of x is just c1 e to the 2x plus c2 e to the negative x. Okay, so I'll put that in a box so I don't lose track of it. That's just the first step, the complementary function. Now I'm going to work on the second step. Now on the second step, I have to figure out an annihilator for the sine of x, right? This is, again, where we could, if we want, we can go back to our table and look for where is the sign of x. It looks like it's number 5 in this table that I'm sharing with you. It's number 5 in the list, but with the little b of 1. So I'm going to take little b equal to 1 in that table. And so coming back to the work that we have here, we're going to use a of d equals d squared plus 1. Now, guys, I'm going to do this one a little differently than the last example because you can shortcut some things. We don't really need to write out applying this operator to both sides of the equation. We already know we're going to get a 0 on the right side when we annihilate it. And on the left side, we actually only care at this point about what the new roots will be. I don't really need to worry about the old roots. The old roots are 2 and -1, and we know that we're going to get those again. But for the purposes of the particular solution, the new roots are what will generate that, which is what step 2 is about, right? We're trying to come up with the particular solution that we're going to use. So I don't really care about the old roots. So I'm not going to write them down this time. I'm going to just shortcut the process and write down the new roots. The roots of this, so d squared plus 1, if you think about what the solution is to that, you're just going to get r equals plus or minus I. So we have to use imaginary numbers here, right? Imaginary numbers. You can also, if you need to, you can use the quadratic formula to get it. But I think d squared plus 1, most people know the roots of that are I and -I. Remember, when you have complex roots, they always come in conjugate pairs, like what we see right here. Conjugate pairs here. So plus and minus I. So let's write down the particular solution. Actually, what I'm going to write down first is the form of y sub p of x. When I say the form of it, I just mean with the constants not solved for yet, because we haven't really solved for them yet. So this takes us back to Tuesday. When we get imaginary roots, we have to remember what terms in the solution do we get? Like, what do they look like? So you remember from Tuesday, that if you have roots of the form a plus or minus bi, well, then you get a solution that's e to the ax times cosine of bx, and e to the ax times the sine of bx. Now in this case, the a is 0, right? There is nothing in front of that I right there. So a is 0 and b is 1. So my solutions are going to just be cosine of x and sine of x. That's it. I'm going to write it this way. Capital A times cosine of x plus capital B times the sine of x. This is the form of the particular solution. Again, I'm not using C3 and C4 because I want to remember that these constants, A and B, we can actually solve for them. Okay? Is everybody with me? I'm counting on you guys to remember from Tuesday, when we get these imaginary roots, it leads us to these sines and cosines, right? And each of those terms has a constant in front of it that we can solve for. Now, guys, sometimes in the homework and sometimes in the midterm, I'm going to only ask you to give me the form of the particular solution. You have to read the questions very carefully. If the question says, find the form of the particular solution, or if it just says, don't bother to determine the constants in the particular solution. If those are the instructions, you stop right here. This is step 2, and you're good to go. Okay, so that's why I was emphasizing this is the form of the particular solution. Why would I not always want you to solve for capital A, capital B, whatever the letters are? Well, first of all, it's a lot of messy algebra sometimes. And what if my differential equation wasn't second order? What if it was like ninth order, right? If your differential equation was a pretty high order differential equation, then to solve for the constants, you would have to take all of those derivatives of your expression. Oh my, that could be extremely tedious. And I'm not interested in watching you guys go through a tedious and excruciating exercise of doing calculus and algebra to solve for these numbers A and B. I'm much more concerned that you understand the process that's going on here, okay? So unless it's a small problem with like not very many constants and a pretty low order of a differential equation, you'll probably see questions that just say, find the form of the particular solution. And if it says that, you're good to go right here. This is step 2, okay? In this case though, let's just go ahead and solve for A and B. It's not so bad on this problem because I only need 2 derivatives, and it's not very hard to take these derivatives. So if I actually take the first derivative of my y sub p, I'm going to get negative a sine of x plus b cosine of x. And then if I'm going to need to take another derivative. I always like to just take all of my derivatives first, just so I can kind of collect them together. The second derivative here would be negative a cosine of x minus b sine of x. So something like that, right? And now I'm going to come back up here. And I'm going to plug these various derivatives into the left side. So the second derivative, so this is where I'm doing the plug in. The second derivative is negative a cosine of x minus b sine of x. Okay, and then we have minus the first derivative, which was negative a sine of x plus b cosine of x. And then minus 2 times the original y sub p, which is a cosine of x plus b sine of x. And this is all equal to 10 sine of x. Okay, I'm hoping that that's legible. Okay, so that's all equal to 10 times the sine of x. Let me erase down here. Remember, I don't want to lose track of my complementary function because we need that in step 3. So what I'm going to do with this big mess on the second line of my board now, I'm going to combine together all of the cosines, and I'm going to combine together all of the sines on the left side. So the right side is 10 sine of x, right? We've got that part down. What is on the left over here? Well, let's figure out where all of my cosine of x's are. I have a negative a right here. That has a cosine on it. And here's a b that also has a minus in front of it. And then here's a negative 2a. So I can kind of look at what are all of the terms that involve cosine. And I see that there's negative 3a of them and then minus b of them. So I'm just going to kind of combine the cosines together like that. And I'm going to do the same thing with the sines. Sine of x, let's see, I have negative b right here. I have positive a sine of x's right here. And that very last term over here is negative 2b times sine of x as well. So it looks to me that there's a positive a right here, and then there's minus 3b. So I'm just grouping the sine terms together and the cosine terms together. And the reason to do that is now when you look at this whole equation on the left side and the right side, we can match up the corresponding coefficients for the sines and cosines. Notice that the right side has no cosine. Well, that just tells me that this term has to be 0, right? And there is 10 sines, so a minus 3b has to be 10. So what we now have is sort of like 2 equations and 2 unknowns. You can put it into a matrix if you want and solve for it. I'm just going to tell you the answer at this point, and I think you can check it pretty easily. A has to be 1, and B has to be -3. So you can plug those numbers in, and you see that it satisfies both this equation and this equation. So after you solve for that, we can write down the particular solution now, which would be cosine of x minus 3 times the sine of x. This is the particular solution. I'm going to put a box around that one as well. Okay, so this is just a times cosine of x plus b times sine of x, right? That was the original form of y sub p. Now, if you guys are good and you follow my instructions and you put boxes around the complementary and particular solutions, I am okay in step 3. For step 3, I guess I can erase this right now. I am okay on step 3. Some students asked me this many semesters ago, and I couldn't really disagree. It's like, why do we now have to write it all out again? So I'm okay if you don't do that, as long as you just simply write this down. Y sub c of x plus y sub p of x. And there should be 3 boxes though. I don't want to have to go like fishing around on your work to find everything. So make sure you have your complementary function in a box, your particular solution in a box, and your step 3, make sure you wrote it down at least in this form so I know that you remembered that you have to do step 3. Okay? Great. So we've taken care of another example. I want to just do one more example. I have about 5 minutes. I'm going to try and at least do part of one more example. Okay? Are there any questions here? There's just 1 or 2 more quick things I need to say about annihilators, and then we are good to go. All right? Okay, so we'll do this one even faster than the last one, I promise. Okay? So this is the last example for today, but you're going to want to watch it because it's going to have some things in it that we haven't covered yet. So solve d squared minus 4d plus 5 of y equals 8x e to the 2x cosine of x plus 15x cubed. Okay. Okay, so we're going to do this one on a sort of a rapid solution. I'm going to try to get to some of the highlights of it. Make sure everybody's had a chance to copy that down. Okay, so our last example for the day, and then we're in great shape. Step 1 is to just write down the auxiliary equation. I'll just write 1 here. R squared minus 4r plus 5 equals 0. That's my auxiliary equation. Very easy to just change the d's to r's. And if you solve for the roots of that, I will skip the details, but it comes out with imaginary roots 2 plus or minus I. Okay? So my complementary function is just C1 e to the 2x cosine x plus C2 e to the 2x sine of x. Okay? That's just straightforward. Again, I'm using, remember, we have imaginary roots here, so that's why we're getting these exponentials with sines and cosines. The power of 2 comes from the real part of the root, and the 1 in front of the x right here and right here is coming from the fact that there's a 1 in front of that I. Okay? Now, let's look at the second step. This is where there's something interesting I want to point out. On the right-hand side, we have two terms. If we go back to our table, we can find the annihilator of this first term. I'm going to just tell you what it is. It's just on that screen that I was sharing with you. That annihilator is, it turns out, it comes out to d squared minus 4d plus 5 quantity squared. Okay? On the other hand, though, guys, 15x cubed also has an annihilator. Remember, by the way, we don't have to worry about the 8 and we don't have to worry about the 15. But x cubed, how do we annihilate that? That's just 3 powers of x. I can annihilate that with d to the 4th. So I have two annihilators for these two terms. And what I wanted to point out is that you need to multiply them. This is very important. Even though there's a plus sign in the form of the right-hand side function, the individual annihilators must be multiplied down here, okay? They must be multiplied. Okay, so this first one is from the table, really easy. This one is just coming from annihilating x cubed. It's actually also in the table. So my new roots, just wrap this up very quickly. My new roots are 2 plus and minus I, 2 plus and minus I, 0, 0, 0, and 0. Those are my new roots. Notice that this quadratic is the same as this quadratic. It's actually, this is not just the first and second time that we're seeing these two roots. It's the second and third time. And we have to remember that when we go to write down the form. This is the last thing we're going to do. The form of the particular solution, we have to make sure that we stack those x's. So what is the form? Let's just write it down and then we're going to call it a day. We don't even need to bother with step 3. I just want to get this form written down. On a problem like this, I would only ask you for the form. Okay, because as you're going to see in a minute, the function is crazy. You don't want to have to take the derivative of it. So what's the form? Well, these two terms are being repeated. So I'm going to write a x e to the 2x cosine of x plus b x e to the 2x sine of x. That's coming from this first pair, right? Because this is already a repeat of roots that we originally had. So I have to stack these x's here. Now, I have another copy of 2 plus or minus I. So I have two more terms that have even more x's stacked. So I'm going to get c x squared e to the 2x cosine of x plus d x squared e to the 2x sine of x. Hope that that's coming in on the bottom of the board there. Okay, so these x's are stacking up because these roots have been repeated 1, 2, 3 times. Okay, and then I'm not done because I have the 4 zeros. Right? And it's like, okay, well, what terms do those go with? Well, there will be a capital E that just goes with e to the 0, right? And then plus, I have to repeat the 0 root, so I'll say fx. I have another repeat, I'll say gx squared. And I have one last repeat, which is the fourth one. That's going to be hx cubed. This is a crazy particular solution. There are 8 constants in it. I wouldn't wish my worst enemy to have to solve those 8 constants, because it would involve taking, what, 2 derivatives of this horrendous mess. And it is pretty horrendous. You'd have to use product rule after product rule. You'd have to have an incredible amount of patience. It would be easy to mess it up. I would never ask you on a problem like this to do more than just give me the form of the answer. Okay, so this would be step 2. And then of course, step 3 would just be y sub c of x plus y sub p of x. Just be sure to put this into a box. Does everybody understand how I got the particular solution here? This is the key step. Okay, well, that's it. We've done 3 examples of this annihilator approach. You can watch those other YouTube videos I have. I think I have some additional examples on that as well. Or if you're feeling pretty good about it, just go ahead and try the homework for Tuesday. I'll take questions on it on Tuesday, and we'll actually try to finish we're going to finish chapter 8 on Tuesday, so that'll be great. Thanks for your attention today, guys. I appreciate it very much. It's great to see all of you. I hope that you're doing okay and staying safe, and I look forward to getting together with you guys again real soon. I'll be over in my office hours later tonight. Feel free to stop by over there, and we'll talk again soon. Bye for now.
Thank you, Professor.
You're welcome. Take care, guys.